Motion-aware gradient domain video composition. We present a novel video composition approach to tackle the problems of ambiguous boundary, motion blur, motion differences, and temporal coherency in video composition. Given it an input target video sequences and source video sequences, several pre-processing steps are first applied. These include optical flow calculation, video segmentation, and video stabilization. The user then inputs a blending trimap on the first frame of the source video by drawing loops and strokes. The user also positions the source object on the first frame of the target video. The system will automatically align the camera and object motion for all other frames. Next, the system will compose an output video using motion-aware gradient domain composition. Our method first optimizes the blending boundary to reduce the flickering near the boundary. Then, coherent mixing of the source and target gradients takes place to reduce the artifacts caused by different motions in the source and target video. Next, we apply temporal consistent mean value coordinate hybrid blending. Consequently, the user can interactively edit the object motion. We illustrate some details of our algorithm here. Our blending boundary optimization minimizes the spatial temporal appearance and motion mismatches. To iteratively compute the temporal appearance mismatch, the boundary on previous frame is projected to current frame according to source and target optical flow. For a point P, a shortest distance is computed to this projection, which also reveals a corresponding boundary point on previous frame. Similar process can be done with the next frame. We minimize the difference of the mismatches with the shortest distances as penalty. We also present an MVC approximation for real-time single-frame hybrid blending with dynamic boundaries. For each vertex X, we pre-compute the angles and tangent values using MVC to a fixed outer boundary. When a new blending boundary is optimized inside, we find a correspondence between the two boundaries. To find the MVC instead of using the angle and tangents to the real boundary, we use the pre-computed tangent values to the outer boundary. This ensures the real-time performance for MVC hybrid blending with dynamic boundaries. Next, we demonstrate our user interface. After pre-processing, the trimap provided by the user on the first frame is propagated to subsequent frames. During this propagation, the user can interactively refine each trimaps. After generating the trimaps, the user sets the gradient mixing parameters, positions the source object in the first frame, and starts the video composition. The source object is automatically aligned with the target video. A curve which visualizes the object motion throughout the frames is shown to the user. The user can adjust the control points to edit the object position, which affects the speed and motion trail of the object. The composition result on current frame is updated to the user in real time. The video composition is updated segment by segment while the user is still editing, and its progress is visualized on the motion curve. The user can lock control points to prevent undesirable editing propagation and unnecessary blending recomputing. With this interleaved editing blend scheme, the user can usually view the video composition result immediately after editing. This shows we edit the jitter magnitude of the boat. To demonstrate the effectiveness of our blending method, we compare it with various previous works. All results were applied after video stabilization and our motion editing. We first show matting and alpha blending result. Note how the surrounding details are lost and the illumination is inconsistent. Next, we show a frame-by-frame blending result with a fixed blending boundary. The lack of the temporal coherence and inconsistent motion along the blending boundary is apparent. Then we show a 3D pose and blending result. Although it is temporal coherent, the motion differences are still visible. This is a result of seamless video composition using optimized mean value coning. This method cannot maintain temporal coherence well for moving scene. Reliant matting can also lose details. Our composition result is not affected by such artifacts and is achieved at an interactive rate. These are more comparisons. Lastly, we show more of our video composition results, featuring ambiguous object boundaries caused by shadows, smoke, dust, motion blur, etc., and demonstrating complex motions of both camera and objects.